Hello everyone, this is Jordi Sastre. I'm a PhD student at TEMPA, the Swiss Federal Laboratories for Material Science and Technology. And in this talk, I would like to present our work investigating the chance transfer across the LLZO solid electrolyte lithium cobalt oxide cathode interface in a thin film model system. Let's get started. Thin film solid-state batteries are a type of solid-state battery consisting of thin film layers which are stacked together to form a battery. These layers have a thickness in the micrometer range and are normally deposited by vacuum deposition processes. These devices were first investigated by Oak Ridge National Labs in the 90s and have become a commercial product that finds applications for powering low-power microelectronics. For example, wireless sensors, smart cards, wearable implantable devices, or anything that requires a low-power source on chip. These systems are also very interesting scientifically to investigate interfaces. This architecture is an ideal 2D system of the battery components, therefore providing a much simpler interface structure and giving much easier access for investigation of such interfaces. For example, in this work, we investigated the interface between the LLCO lithium garnet solid electrolyte and a common cathode lithium cobalt oxide in such a model system. The lithium garnet LLCO solid electrolyte has become popular in the research community and also in industry because of its advantageous properties, with ionic conductivities above 1 millisiemens per centimeter, and most remarkably, it has a wide electrochemical stability window, being stable against metallic lithium and high potential cathodes. Moreover, its thermal and mechanical stability make it a promising material for building safer solid-state batteries. On the lab bench, they are typically processed in the form of millimeter-thick ceramic pellets, which are sintered at temperatures of about 1200 degrees Celsius for prolonged times. But if you want to build this material in the form of a thin film, for constructing a thin film battery with LCO, we face several challenges. In this chart, I summarize the typical processing temperatures for thick pellets and sheets and thin films, vacuum processed thin films. What we observe is that typically thin films are processed at much lower temperatures, 400 degrees below the standard temperatures for pellet sintering, but at the same time, they also show much lower ionic conductivities, from 1 to 2 orders of magnitude lower. The challenges of thin film LLCO processing are the high surface to volume ratio that leads to a massive lithium losses during the deposition and sintering step. This forces one to lower the processing temperature, and of course, this has an impact on the density and homogeneity of the films. Also, higher surface to volume ratios make these films much more sensitive to air or any kind of surface degradation. Overall, this has a significant impact in the ionic conductivity, with maximum values achieved in the 10 to the minus 5 siemens per centimeter range. In our work, we investigated an RF magnetron sputtering process to fabricate LLCO thin films with equivalent properties to the bulk pellets. We used an stoichiometric LLCO target, which we spotted in argon and oxygen to form an amorphous LLCO film on a substrate. Here, the XRD shows the amorphous phase of the as deposited films. In order to crystallize them, we process these films in oxygen at 700 degrees for about 1 hour in order to crystallize it. However, due to the lithium loss occurring both during the sputtering process and the annealing process, what we observe in such films is the formation of non-conductive lithium-deficient phases, specifically lanthanum seconate. In order to compensate the lithium losses and achieve a pure LLCO crystalline phase, we included an additional source of lithium, a lithium oxide target, which is co-sputtered during the deposition process. With this, we are able to achieve a pure crystalline LLCO phase. Pure LLCO crystallizes in a tetragonal phase at room temperature, which is not a good ionic conductor. In order to become a high ionic conductor, it requires the addition of a substitutional element, for example, aluminum or gallium, that stabilizes its cubic phase at room temperature. We investigated the addition of these two substitutional elements and their impact in the crystalline phase and the microstructure. Here on the left, we have the XRT plots of the pure LLCO, the aluminum substituted LLCO, and the gallium substituted LLCO. We observe that in both the aluminum and the gallium doped LLCO thin films, we obtained a pure LLCO cubic phase. We also observed in the microstructure that the addition of such a substitution element has an impact in the densification of the films, especially those with aluminum. Also, the degradation on the surface seems to be mitigated by the addition of substitutional element. With this process, and by adding substitutional elements like gallium and aluminum, we could push up the ionic conductivity values for LLCO thin films while retaining a low processing temperature of only 700 degrees. Especially with gallium substituted LLCO, we were able to achieve an ionic conductivity of 2 × 10⁻⁴ siemens per centimeter, which is equivalent to what has been reported for standard LLCO pellets. Now let's talk about the LLCO cathode interface. It is well known in the solid-state battery community that the interfaces of oxide materials with the electrodes are very problematic. For example, the LLCO cathode interface suffers from high interface resistances because in order to form a proper bonding between both oxide materials, LLCO and lithium cobalt oxide, for example, one needs high temperature co-sintering. And this leads to interdiffusion process and cross reactions that occur at the interface and form an ion blocking interface. Therefore, it becomes necessary to do some interface engineering to prevent such a cross reaction process. And our question was, could we use a thin film model system to better understand the degradation process occurring at the interface and to use this system as a playground for interface engineering? Utilizing the thin film LLCO process previously described, we built then an LLCO-LCO model system in the form of thin films, which provide an easy access to the interface for characterization. For example, by grazing zinc XRT, we could characterize the phases of the decomposition products forming at the interface. Besides the LCO and the LLCO phase, we observed this lanthanum zirconate phase, which is a sign of degradation of the garnet phase. We also looked at the elemental distribution around the interface by time of flight secondary ion mass spectroscopy, TOF-SIMS, and we observed that zirconium and lanthanum are diffusing into the cathode, and cobalt is also diffusing into the solid electrolyte. This model system also allowed us to investigate interface modifications to prevent such an interface degradation process. We introduced a 30 nanometers atomic layer deposited niobium oxide interlayer, which then is in situ lithiated during the co-annealing process. With this interface modification, we were able to obtain pure LCO-LLCO phase without any secondary phase, as we can see here in this XRT plot, in comparison to the already shown bare LCO-LLCO interface. Also, looking at the elemental distribution acquired by TOF-SIMS, we observed that the interface is capable of blocking the interdiffusion of lanthanum and zirconium into the cathode and cobalt into the electrolyte. We also characterized the charge transfer properties of the interface in the half cells. Here on the left, we have the Nyquist plot of the EIS measurement of the LCO-LLCO half cell without any interface modification. We observe an interface resistance in the order of 5 kilo-ohm square centimeter. On the right, we have the Nyquist plot of the EIS of the interface modified half cell, and we observe that the interface resistance drops to values of only 50 ohm square centimeter. This demonstrates that the interface modification that we investigated, this lithium niobate interlayer, significantly mitigates the formation of ion blocking decomposition products at the cathode electrolyte interface. We also investigated the charge-discharge characteristics of these half cells consisting of LCO and LLCO and compared it to bare LCO in liquid electrolyte. What we observed is that an interface modified LCO-LLCO half cell is capable of delivering about 140 milliamp per gram, which is about it's close to the theoretical capacity of the cathode, whereas the non-modified LCO-LLCO half cell delivers less than a third of the theoretical capacity of the cathode. We also investigated the rate performance of such a half cell. The modified half cell, the interface modified half cell, shows comparable rate performance to the bare LCO up to 10C, but then at 20C and 40C, the capacity drops probably because of this added resistance. On the other hand, the non-modified half cell shows barely no capacity at higher rates than 1C. We also assessed the long-term cycle life of such a half cell, and we were able to achieve a cycle life of around 138 cycles at 10C. So with this, I would like to conclude my talk. I've shown you that thin-film solid-state battery architectures are useful model systems to investigate interfaces. We developed a method for fabricating LLCOs in films with equivalent properties to the bulk material. Specifically, we were able to demonstrate ionic conductivities of 2 × 10⁻⁴ Siemens per centimeter in a 500 nanometers gallium doped LCO film. With this fabrication process, we were able to construct an LCO thin film model system that we employed to investigate the degradation processes occurring at the interface upon co-sintering. And we also used as a playground to investigate interface modifications. Specifically, we introduced a lithium niobate interlayer that is capable of reducing the interface resistance from 5 kilo ohms square centimeter to only 50 ohms square centimeter. These thin film architectures also allowed to demonstrate that fast charge transfers are possible between LCO, solid electrolyte, and a cathode material. If you are interested to learn more about our work, you are welcome to check these references. And with this, I would like to thank you all for listening to this talk. And if you have any question, please just write me down here in the Q&A or just drop me an email. Thank you very much.